After that, we'll take another step in statistics where we'll talk about descriptive statistics. So when we talk about descriptive statistics, in descriptive statistics, we try to represent the data in the form of graphs or maybe some kind of different graphical formats, like maybe histograms, maybe line plots, line graphs, scatter plots, right? And based on that representation, we'll come up with, and that particular data being represented based on some kind of central tendency. Okay, means that particular graph might be representing distribution of the mean, might be representing distribution of the measures of the spread, right? So it all depends on what kind of data, what kind of analysis you are dealing with. So in order to do that, we have few of the measures of the center, or you can say central tendency. That measures are nothing but the mean, median, and mode. So when you talk about mean will give you basic central tendency about the whole group. Let's say if I'm talking about the average marks scored by each and every student in school A is 90%, then that particular data will give us a meaning, or you can say an information about the whole school, that on an average, each individual student of the school scores around 90%. So it gives us a central tendency that the school performs normally well. So like that, we have mean, we have median, we have mode data that can be used in different kinds of analysis in order to get the central tendency of the whole population. Okay. So if you try to understand the meaning of all those terms, let's take a look at this example. Here we have a sample data sets of empty cars containing the variables called cars, miles per gallon, cylinder, displacement, horsepower, and things like that. Okay. Now, one by one, we'll try to come up with these measures of the centers. And let's say if we, for example, we need to find out what is the average of the horsepower, how to find average of horsepower, how to find common type of cylinder, how to find center value among miles per gallon entries. So let's say start with an analysis number one. Here we want to find out the most common type of cylinder. So when you say most common type of cylinder, and you see the value of the most common type of cylinder are divided into two types, like 4 and 6. And if you try to calculate the mean, man, which is nothing but taking the average out of the whole records. So coming back to the first analysis, we're talking about the most common type of cylinders. We got the two values like 4 and 6. So if you see, the frequency of 6 is more. So you can say, we can predict that, okay, most common type of cylinder is 6 cylinder. If you want to find out the average horsepower of the cars among the population of the cars, now in this case, we'll calculate the average, or you can say mean of the all the values of the horsepower. So we'll get the average value of the horsepower in the whole sample population. Then let's say we need to find out the center value of the miles per gallon among the population of the cars. How to get the central value? We can get the central value with the help of median of the whole data set, which is nothing but we'll try to take the two. If the number of the entries are even, then we need to consider two entries. If it is odd, then we can take the middle value. Okay, that's what they're doing here. Now, in order to represent the same thing in R, this can be done pretty easy. Let's take a quick example with the help of RStudio. If you try to see, we just have sample for mean. Let's see if we can do that. We take the sample, right? We got the sample. If you want to calculate the mean, it's a simple direct function is available. So we can directly create the mean like that. If you want to check the value of the mean, you can simply say the value of mean is this. Okay, right? You can see the mean is something around 10.14. So that is how you can actually calculate mean. That is how you can calculate the median. That is how you can calculate the mode. We have different functions written for that, right? If you try to see for mean, median, mode, you can see. So mean, you already know how to create. Median also direct function available. In order to get the mode value, which is nothing but the most frequent values present in the whole dataset points, we can define our own function in R with the help of like this, get more than the function, and we can get the unique set of values. We can get the maximum of the occurrence of the values, and then the result will give us the mode of the whole data set. And we can actually represent the data set with the help of histogram. So in order to do that in R, you just have to use the function called hist and pass on the parameters. So that's how we can calculate the median in R. So direct function available. So if you go by the mathematical definition, you can see it's nothing but take the two values, middle values, and get the, if it is odd, then you can get the direct value. If it is even, you can have to take the two values and divide it by 2. Similarly, mean, take the sum of all the values divided by the number of the values, and mode is nothing but the number of the frequent, highly, or you can say the most frequent number. That's what it come as mode of the whole data set. Like measure of the center, we have another thing called measure of the spread, right? How can you measure the spread of the data? So there are 4 terminologies used there. One is called as range, one is called interquartile range, another is variance, another is standard deviation. So range, as the name suggests, it is giving you some kind of a, you can say, whole sort of values between 2 points like max and minimum. So if we take the difference between max and minimum, we ideally will get the value of the whole range, and that is called as range of values. So in some of the in some of the libraries, you will see there are direct functions available in order to get the value, maximum value of data set points, at the same time to get the minimum value. Once you take the difference between the maximum value and the minimum value, you'll get a whole spread of values, and we call it as range. Similar to the range, we have quartiles as well. So instead of getting difference between max and minimum, we'll try to divide the whole data set into some kinds of quarters, and those are called as quartiles. If you see the slide, we have divided the set of 10 points into 3 quarters. Okay, that is how we can divide the whole set again in terms of quarters. If you see this example, we are again dividing into different quarters because we have 100 values. The quarters will be lying between 25th and 26th, 50 and 51st, and 75, 5th and 76th. That's how we can calculate the quartiles. Now there is another term called interquartile range. So range, we already know the difference between max and min. Interquartile range, as the name suggests, it's the distance between the quartiles, right? So say for example, if you wanted to have a interquartile range between quarter 3 and 1, so we'll normally take quarter 3 value minus quarter 1 value. That will give you interquartile range. Apart from interquartile range, there are 2 more important terms. One is called as deviation, another is called as variance. So both of these terminologies revolves around the calculation of mean. So basically, they will tell us how much each data is varying from the mean, and we call it as variance. And difference between each value of the mean is called as deviation, and different, or you can say the deviations and entails computing square of deviation is called as variance. So basically, how it is being calculated is, since we need to calculate the variance of the whole data set or the whole population, so first of all, we need to calculate the difference between the set point and the mean value. And then one by one, we need to add for all the data sets points available. And then we need to square it so that we cannot cancel out the difference which may be assigned results, right? That's why we squared it. And then we took for the whole sample, divided by n-1 in the case of sample variance. Why sample variance n-1? Because later on you will see in some of the further classes there is a term called degree of freedom, and that degree of freedom we need to subtract from the number of the samples in order to get the exact value, in order to take into consideration you can say the units of error, you can say additional variability that may be missed if you take all the n samples. And then the population variance is nothing but the set of population and the population mean, and the same formula as it is for the sample variance. So as I told you, variance is a measure of the spread between numbers in a data set. It measures how far each number in the set is from mean. Similarly, for deviation is a measure or a dispersion of a set of data from its mean. So basically, variance is at an individual level, and the deviation is to the whole data set point. If the data set points are far from the mean, if they are very much far from the mean, then the deviation is very high. Let's take a look at this example in order to understand standard deviation. So say for example, Sam has 20 rose bushes. The number of the flowers on each bush is 9, 2, 5, 4, 12, 7, 8, and 11, and few other values. Now we need to calculate the standard deviation. So first of all, in order, as I told you, that standard deviation and sample variance revolves around the mean values. So first of all, we need to calculate the mean value. So here in this case, the mean value is 7. Then we need to calculate the difference of each point with the mean value, square it, and then sum it all. So that's what we are doing in this step. We are squaring each individual value. Last step, we are summing it all. And then we are dividing with the n-1 sample or total sample. And then you will get a result that the square difference is 8.9. And in order to get the standard deviation, you will get as 2.983 is the standard deviation of the whole data set. So in order to represent the same thing in R, we already saw, we take the sample values and then we create a histogram in order to represent that. So let's quickly run this example. Get the histogram. This is something like this histogram you will get. So this is the initial set histogram, then we calculate the mean value. In order to print the mean value, we'll print the mean variable, we'll get the mean value, we'll print the median value, and then we define the function for getting a mode value, okay? And then we store the value in the result function, result variable, we'll print the layer of the mode, we'll get the mode values like this, right? So that's how we can actually do the same stuff of calculating mean, median, mode in R, okay? And at the same time, we can draw the graph as well. So in order to calculate the range, as I told you, right, most of the languages supports the calculation of maximum value and the minimum value to the whole data set point directly with the help of some of the APIs. So those APIs are max and min here in this case. So max data minus min data will give you a range. And if you wanted to calculate the variance of that value, just call a var function. It will give you the variance of the whole data set point. All right. So another important term in this course is information gain and entropy. So before we go into the details of information gain and entropy, first of all, you need to understand what is meant by purity or what is meant by impurity. So if you're from the scientific background, you might have heard this term called entropy in case of physics, where entropy is a measure of uncertainty in the data. So what this physics term is doing here? So this can be explained very beautifully with the help of one example. So let me explain you that example and then we'll come to the formal definition of these terms. Let's see. I have a use case where a match is going to be played on specific days. The task is to forecast whether the match will be played or not according to the weather conditions. So we need to make a prediction here. And for that, we have a data set available with us, which is having like 14 values for each day. And that has few of the parameters like outlook, which may be sunny, overcast, rain. And we have humidity, which may be high, normal. And we may have wind, like strong wind, weak wind. And based on all these factors, whether we can play or not. So if you take a look at this one, there are total 9 yes and 5 no's. That means there are 9 outputs that suggest us that the play will happen, and there are 5 no that suggest that play won't happen. So based on the different properties of the outlook, we divided the set into 3 further divisions, right? Like sunny, overcast, and rain. Now you must be wondering, why did I choose only outlook, right? So let me answer that question shortly. Let's first try to understand what exactly is information gain and entropy I'm talking about. And then gradually you will understand where we can use entropy and information gain and why we have chosen only outlook as a end result feature to be taken, not humidity and wind. Let's imagine we somehow got to know that outlook has to be taken. So if you take outlook, we get 3 different results there. It may be outlook may be sunny, it may be overcast, and rain. So if we talk about outlook as sunny, you will get again 3 different results, or you can say 5 different results, where 2 of them are suggesting that play can happen and 3 are suggesting that play may not happen. Then if you go with overcast, all of the data set or all of the entries suggesting that play will happen. If you go with the rain, then there are 3 suggestions that play will happen and 2 suggestions play won't happen. Now, if you go into detail, this is an example taken from the decision tree algorithm, right? So if you see, initially we started with some kind of a mixed data. We don't have correct information available with us. Based on that, we can say the play will happen or not, because there is a mixed data. Because 9 years we started and 5 no. That kind of data we call as that has impurity, because there is no final resolution we can make on the basis of that those values like 9 years and 5 no's. Similarly, if you take sunny data, there is the same problem with this one because there are 2 years and 3 no's. Similarly, if you take rain, the same problem is there as well with 3 years and 2. But if you take the overcast is completely pure data. When I say completely pure data, that means there is no chances of confusion here, and you can blindly go and say, okay, the play will happen. That kind of data is called as pure data. Now, if you think, how can you calculate the entropy or the disturbance? That is a very simple formula where we try to calculate the probability of getting those values. So the probability of getting yes and probability of getting no, we divide with all those terminology, simple mathematical formulas there. And once you get, so it will give you a total entropy for that combination, which is 0.94, which is very high. So based on all this calculation, so if you go back to the formula, if you see the same formula we have applied there. So as I told you, it is a measure of uncertainty. And in fact, based on the value of entropy, you can calculate the information gain. Now, if you see in this example, we have started with the entropy of 0.94. We have just calculated. So here we have, you can say, I'll just represent entropy with E. So here we have entropy of 0.94, right? Okay, and if you see here, we have pure data set. So we have 100% information gain here. So how can 100% information gain, which is nothing but Ig, some value of entropy, and minus something other value of entropy. Here we don't have any entropy value because the number of no's is zero here, right? So we'll probably get zero value. But here, if you see, if you calculate the entropy here, you will get some value of entropy again. And then differentiating that initial value of entropy with this value of entropy, you will get some differences. That will give you the information gain value. So I'll show you shortly. Just now, why I told you all this about information gain and this one. So ideally, we always want 100% information gain. We don't want to lose our data on the entropy values. So we need to choose a better one that will give a 100% information gain. We should not lose the data while taking decisions. So out of all the combination like sunny outlook, windy and humidity and other things, right? Why we have chosen outlook and that too with all these values, right? So if you we'll start with calculating the information gain in each and every case. So information gain in case of windy, you can see here. So entropy for the initial set we all know, which is 9 years and 5 nodes, which is common to all of the combinations. We'll get the entropy of the initial system is 0.94, and then we calculate the entropy for the other combination that we are taking into account, right? So you'll see the difference information gain is 0.04, which is very less, right? So you want the more information gain. You go to the another combination, and here you will see 0.94 minus some other combination that we have taken for outlook, right? And you will see the here the difference of, or you can say the information gain that we're getting is 0.24, which is bigger compared to 0.048. That means in an outlook, if we consider outlook as a parameter, we're getting better information gain compared to the windy one. Similarly, in case of humidity, the calculation of information gain as per the formula gives us 0.015, 0.15. So that is again better than your windy, but still less than your outlook. So outlook is the one. Similarly, we take temperature as well, but still has a very low value. So outlook is the one which gives us a very good information. That is why we have chosen outlook as a measure to start with a decision tree, right? Because we're getting the maximum information gain. Now let's come back to the last topic called confusion matrix. So confusion matrix is again a very straightforward method to calculate the performance of an algorithm, and basically that is classification algorithm. It's used pretty heavily, and it works on the concept of true and true positive, true negative, false positive, and false negative. Let's try to understand confusion matrix with a simple example. Now here what we are doing, we are having information about 165 cases of patients. Out of 165, 105 have the disease and 60 patients do not have the disease. And the classifier predicted 110 times as yes and no as 155 times. So now we have to come up with the measure of the performance of this algorithm or the model that you have fit for that. So we'll try to create a matrix of yes, true positive, true negative, false positive, and false negative. That means when it is predicted no and there is actual no, how many cases that we have done that? Which is 50. When there is predicted yes, but there is an actual no, that means 10 times. When there is an actually yes and we predicted no, we made it like 5 times. And there is an actual yes and we predicted yes, there is 100. So we create a matrix, something like matrix structure. And we call those matrix values with predicted and expected values based on our prediction is correct or wrong. So if we talk about the true positive, that means there are cases where we have predicted yes and it was actually yes. That means we have predicted that they have disease and they actually have disease. Then we have true negative when we have predicted as they don't have disease and which is the true and they actually don't have disease. When there's a false positive when we predicted that yes they have disease but they actually don't have disease. That is an error or mistake we did. Then we have false negative, we predicted no. Actually, they do have disease, right? So that is another way around. We again made an error in that case. So based on all those calculation values of true negative and false positive, false negative, we come up with the two terms called sensitivity and specificity. If you see, these are the terms that we talk about, right? True negative is nothing but a predicted no and actual no. True positive is predicted yes and actual yes, like that. We divide it into some kind of matrix form. And then we calculate the sensitivity is nothing but probability of detection of some fields, that is measure of the positive, right, which is nothing but true positive divided by the combination of true positive and false negative. Okay, and that means it gives you a fraction of all those with the disease who get a positive test result. Similarly, specificity gives information about the true negatives, right? Which is nothing but true negative and the false negative, false positive, and you get some value of that. It will give you a fraction of those without the C. So basically, while doing all this, we get some of the additional information, because if you go with the other accuracy measures where we just calculate the error and we see how many of them is predicted correct and how many of them are predicted wrong. Instead of getting those accuracy measures with confusion matrix, you will get an additional benefit of seeing the behavior of your model. How many of them are predicted correctly? How many of them predicted wrong? How many of them are original correct but your algorithm predicted wrong? How many of them original wrong but your algorithm predicted right? Like that. With the help of these terminologies, you can drill down to the further.